Well, welcome to the Crazy Hat Chemist, and here's another awesome video. Good morning, good afternoon, and good evening, or wherever you might be. So here we go. Today we're going to be talking about thermochemistry, and this is an awesome, super cool topic. And so here's a little bit of a summary of what are some of the things that you need to know for this particular topic. So this is one of the basic thermodynamics equations right here. Q equals mc delta T. I always tell my students, do you want to become a doctor? What's the qualifying exam? Well, the qualifying exam is the MCAT, M-C-A-T. This is not really an A, this is a delta, but hopefully that will get you to remember this. Many textbooks have this in a different order, but it's Q equals mc delta T. Q is a heat term that's most commonly as joules, and M is the mass. Cp is the specific heat capacity. The mass is in grams. The specific heat capacity is joules per gram degree Celsius, and the change in temperature. So this delta T is the change in temperature. The change in temperature is the final minus the initial temperature. Okay, so if we substitute in the final minus the initial temperature into delta T, what are we going to get into this equation? We're going to get this equation here. Q equals mCp Tf minus Ti. All right, so this is really, really important. All right, I highly recommend that you go to my YouTube channel and watch my video on this entire unit before you carry on with these worksheet problems. Okay, and this is one of the slides that I have right here, and this is a really important slide for this unit. Okay, and this is a generic heating curve, and it's a temperature on the y-axis versus constant heat on the x-axis. Okay, so really important graph here. And what defines this graph, and this is a idealized version of this graph where these are nice abrupt changes along here. What identifies or what's critical for this graph is that this first flat line is going to be the melting point or the freezing point. And then this second flat line is the boiling point or condensation point. Okay, and so this first slope section, second slope section, and third slope section is going to be a solid, a liquid, and a gas. And then the first flat line, you're going to have the transition between the solid and the liquid. At this point right here, you have a solid at the melting point. At this point right here, you have a liquid at the melting point. Okay. And then at this point, you have a liquid at the boiling point, and at this point, you have a gas at the boiling point. Okay. At the solid, the liquid, and the gas, you should see that the equation for this point here, for the solid, for the liquid, for the gas, has a change in temperature section on each one of those three, because you can see that there is actually a change in temperature. Whereas if you are at the melting point, which is called the heat of fusion, is the constant that you use here, there is no change in temperature in that equation because the temperature is constant. Okay. You're breaking intermolecular forces as you proceed on from a solid to a liquid. And same thing here, you're breaking intermolecular forces as you're proceeding on from a liquid to a gas. And again, the heat of vaporization, that's why you are not having a change in temperature. For water specifically, this first step is a solid. We'll be using this basic equation, Q equals mc, C for the solid or ice, delta T. And the specific heat capacity for ice, which is the solid, is 37.8 joules per mole Kelvin. And then over here, the next step, and I call this step number 1, and this one's going to be number 2. That's why there's 2 here and this number 1 right here. So number 2, we have Q equals mc. There's no delta T again because there's no change in temperature, but the constant is the heat of fusion. The heat of fusion for water is 6.01 kilojoules per mole. And as we proceed on with this graph here, as we are continually adding constant heat, we're moving along this x-axis. It's step number 3 right here. Q equals mc for the liquid delta T. And this is the specific heat capacity for water at 4.184 joules per gram Kelvin. Then as we move on here, this is the heat of vaporization. The equation at step number 4 right here is Q equals mc, the heat of vaporization, and that heat of vaporization constant is 40.7 kilojoules per mole. And then as we proceed on, we're going to be in the gaseous state at step number 5. That's Q equals mc for the gas or vapor, delta T. And the specific heat capacity for steam for water is 36.5 joules per mole Kelvin. The other thing that you need to know here is that you can have the specific heat capacity in different units here, depending on what the substance is. And then one other thing, I do have these in Kelvin, but I do need you to understand that the change in temperature for Kelvin and the change in temperature for degrees Celsius is the same. Since the interval for the Kelvin and the degree Celsius scale is the same, that means that the change in temperature will be the same. All right, so now what we're going to do is we're going to move this on up here a little bit more, and I have a little bit more information. Another equation that we'll be using is QA plus QB. This is most commonly written as Q metal plus Q water. But A and B could be either water and water, metal and metal, or water and metal. It doesn't really matter. There are some textbooks that don't like to have the plus and the equal 0 portion of it. So you can rearrange this and subtract one of these from this left-hand side and then move it over, and then you will get this equation. QA is equal to negative QB. This is effectively saying that as you add two substances together, which have different amounts of heat in them, i.e. different temperatures, then the hot object will lose the energy to the cool object. Okay. If you look at this equation here, or if you look at this equation, okay, then what you can do is substitute in what Q is equal to. And if we just look up here, Q is equal to mc delta T, which is Q is equal to mc TF minus TI. So we're going to substitute in what is equal to Q. And so we'll have mc TF minus TI plus mc TF minus TI equals 0. So I've substituted into this equation right here, and that's why we get this one. One of the key components to this is when you have two compounds, either two amounts of water, two amounts of metal, or metal and water, and you mix them together and they have different temperatures, the hot object will lose the energy and the cool object will gain the energy, and eventually they will reach what is called thermal equilibrium. When you reach thermal equilibrium, that is when the final temperature of both objects is the same, and there's no net heat transfer from one to the other. You'll still have heat transfer going back and forth, but there's no net heat transfer. That is when the final temperature is the same. So if you are given the final temperature for one of them, then you know the final temperature for the other. Or if you are solving for the final temperature of one of them, then you are actually solving for the final temperature of both. Okay, so that's really important to know. Another way that the specific heat capacity for water is written is 75.40 joules per mole Kelvin. And this is per mole as opposed to I had per gram over here. So that's another way that that's written, just so that you're aware, just so that you can work with that as what your textbooks have. And in using that, I'm just going to write one other thing here that's important for this unit here. And if I use that same amount, that 75.40 joules per mole Kelvin, and I'm going to convert that, then I'm going to say 18.02 grams, that's the molar mass of water, is equal to 1 mole. You should see the moles cancel out. And now we will have joules per gram Kelvin, which again, I've noted that the Kelvin and the degree Celsius temperature scale, the interval is exactly the same. If you go up 1 Kelvin, you'll go up 1 degree Celsius. If you go up 10 Kelvin, you'll go up 10 degrees Celsius. So that's why 4.184 joules per gram Kelvin is equal to 4.184 joules per gram degree Celsius. Okay, so that is really important. Another really important concept here is that you must understand that if you have a low specific heat, okay, so like gold has a very high density and low specific heat. And there is an inverse relationship between density and specific heat. So specific heat of gold is very low. Specific heat of aluminum is very high relative to that of gold. And yet the density is very low for aluminum. So there's an inverse relationship between density and specific heat. If you have high density, you have low specific heat. For gold, for example, if you have aluminum, you have low density and high specific heat. So you can actually make a nice linear graph of this, and you should be able to see that relationship, okay? If you have a very low specific heat, then that means that that object acquires heat very rapidly, okay? And also dissipates the heat very rapidly. Okay, so you can heat up a piece of gold very quickly and then cool it down very quickly. Whereas if you have aluminum, it takes quite a bit more energy to heat it up and it will take more time to release that energy. Another important equation that we're going to be using here is the enthalpy of reaction, and that is the delta H of the reaction is equal to the sum, that's the summation of the products minus the reactants. And I usually typically put this around brackets here. That way you make sure that you actually distribute this negative sign over all the reactants. So delta H naught formation of the products minus delta H naught formation of the reactants at standard conditions. These little zeros here mean standard conditions. This is formation of the products, formation of the products. And this is for the entire reaction. So we're also going to be dealing with Hess's law, and that's the sum of the enthalpies of multiple equations. They equal the whole entire sum of that reaction, and this is relative to a state function. All right, so that's just a brief little summary. So what we're going to do now is we are going to actually move on and do some actual problems here. So let me move back to this here. All right, fantastic. So hopefully that gave you just a bit of a summary of this thermochemistry unit. You probably really actually need to be looking at that summary of what I just went over so that you have a good idea of what's going on before you carry on with these mathematical problems. And again, please watch my entire video on this unit because that's going to be helpful as well. All right, so let's get moving on to thermochemistry worksheet number 1. We're going to calculate the heat required in joules to warm 3.2 grams of water from 24.1 degrees Celsius to 85.6 degrees Celsius. I've given you some constants up here. They are the same constants that I just aforementioned in the summary of this lecture. Okay. So what we need to do is I would highly recommend that you draw a rough graph so that you actually make sure that you know where you are along this graph, and that will help you acquire the constants that are required for this. So a rough graph would be the same, like this. So, I mean, you do not have to spend a lot of time on this graph here, and it's a sketchy, dicey graph. It doesn't have to have very much information on it. You should realize that this point here is the melting point. This point right here is the boiling point, okay? And furthermore, since this is water, you should actually know these values. This is 0 degrees Celsius, and this is 100 degrees Celsius for those two. From this, we're going to draw two dots. And those two dots are going to be the low temperature that we're dealing with. And the low temperature is going to be above 0. That's 24.1. That's going to be right here. And then the high temperature is 85.6. That's going to be right here. And then what we're going to do is we're just going to connect the two dots. So really what we're interested in is acquiring this graph right here. So that's what I'm referencing is I'm using this graph Based on this graph and those temperatures, I know what equation I'm using. So the equation that I'm using is Q equals MC for the liquid, delta T, which is TF minus TI. So I know that I'm actually at step 3 of this graph. So that's really the important component to this here. All right. So now that I'm at this section, I know that I'm using Q equals MC for a liquid, delta T. And we're going to replace the delta T with TF minus TI. All right, just like that. So what we're going to do is we're going to plug into this. It says we're going to calculate the heat required in joules. So this is the heat term that's going to be in joules. This is 3.2 grams. That is most certainly a mass. This is my initial temperature, and this is my final temperature. And then this constant is given right up here. Okay, so we're going to be using that constant for this problem. So hopefully that gives you kind of like a summary of where all these numbers are. So Q is equal to M, the mass for this particular problem is 3.2 grams. I'm going to get my ruler out because this is just like a stoichiometry problem in some respects. So hopefully that works for you. Okay, and here we go. We're going to just draw a line there, make it look nice and pretty. Okay, and the constant that we're using is right here, the specific heat capacity for water. And that's 75.40, so 75.40 joules per mole Kelvin. Okay, all right, fantastic. That's looking pretty good. And then what we need to do is we need to cancel out all the units such that we get only the units that we are interested in, which is heat, which is joules. So we're actually trying to save the units, if you will. There's one way of looking at it. We're trying to save the units of joules. So in order to do that, I need to cancel out the moles, grams, and Kelvin. So one thing I'm going to do is actually, I'm going to scratch out this Kelvin term here. We don't really need that because degrees Celsius, like I mentioned earlier here, degrees Celsius and Kelvin has the same interval. So we can actually scratch that out. We don't really need to use it like that. Okay. So we're going to cancel out these moles. So we're going to have 1 mole of H2O, and that's equal to 18.02 grams of H2O. And this is the molar mass for water. This will enable me to cancel out the grams and the moles. Now I have joules per degree Celsius. So we're getting closer to the units that we want. And here we go. Keep on going. So now what we're going to use is the final temperature minus the initial temperature. And the final temperature is 85.6. That's degrees Celsius minus 24.1 degrees Celsius. And then this whole term here is going to be degrees Celsius. There are not 2 degrees Celsius here, right? So it's just degrees Celsius. That's going to cancel out with that. And then we're going to be left with joules. So it's 3.2 times 75.40 divided by 18.02 times the difference between 85.6 and 24.1. And then we're going to have our heat term. The fewest number of significant figures that we have, this is a multiplication. We do have a subtraction here, but we'll put this in parentheses and we'll do that change in temperature, whatever that is. And then we'll plug this into our calculator. We got 2 significant figures right there is the fewest number of significant figures that I have in my problem. So Q is going to equal 820 joules. And that's our answer for this problem. All right, fantastic. So hopefully that worked out well for you. So now we're going to do another problem here. So we're going to slide this on up. And here is problem number 2. All right, problem number 2 says calculate the specific heat of a metal when 21.3 grams sample of metal requires 0.254 kilojoules of heat to raise the temperature from 22.6 degrees Celsius to 105.5 0.7 degrees Celsius. So just like before, we are going to use this equation. Q equals mCp delta T. And again, we are going to remove the delta T and substitute in what it is equal to, which is TF minus TI, right? So just the units on these problems should definitely help you out. It says a temperature from this, so this is TI, because it's from that, it's starting that, to an ending temperature of TF. This is the mass, and then this is the heat term because it's in kilojoules. So you should see that we have the Q term, we have the M mass term, we have the final and the initial temperatures. So we'll get our change in temperature from that. And then we're going to be solving for the specific heat capacity, which is CP. Knowing that this is a metal, our specific heat capacity would be likely to be less than 1. So this is something that you should kind of already know. Right, and specific heat capacities have units that are in joules per gram degrees Celsius most commonly. So those are the units of which I want. So in order to do that, what we want to do is we are going to convert these kilojoules into joules. So that's a real simple thing that we can do here off to the side. So 0.254 kilojoules. Sorry about that bell. Forgot about that. I'm actually at school here. And you're going to hear a couple more bells here in a little bit, unless I can chop those out of this recording here. So here we go. So we're going to convert these kilojoules into joules. So that's 1 kilojoule is equal to 1,000 joules. Okay. So this is going to equal 254 joules. So now I have my heat term in joules. That's going to be important here because our units, like I said, are joules per gram degree Celsius. So now what we're going to do is we're going to plug into this equation right here. So I'm going to have, for Q, it's going to be 254 joules. That's the Q term. The M term is right here. That's 21.3 grams, 21.3 grams. That's right there like that. I'm solving for the specific heat capacity for the metal. And then my final temperature is 105.7 degrees Celsius. My initial temperature, and there's a subtraction here, my initial temperature is 22.6 degrees Celsius. Okay, and again, I am solving for the specific heat capacity. That's right here. That's what I'm solving for. And so what we're going to do is we're going to have 3 significant figures when we do this problem right here. We have 3 significant figures here. We have 3 significant figures here. And when we do the 105.7 minus 22.6, we're going to get, so our change in temperature is going to be 83.1 degrees Celsius. That also has 3 significant figures. Okay, and so we're going to solve for the specific heat capacity. So I'm going to rewrite this whole thing here just in case if this doesn't make sense here, but specific heat capacity, okay, is going to be this 254 in the numerator divided by both these terms. So 254 joules divided by the 21.3 grams and the change in temperature, which is 83.1 degrees Celsius. Okay, and then you should hopefully clearly see the units that are necessary for this problem, which are joules per gram degree Celsius. Again, I have 3 significant figures, so we're going to get a specific heat capacity of 0.144 joules per gram degree Celsius. And again, since this is a hunk of metal, a piece of metal, I should be getting a specific heat capacity that is most certainly less than 1. That number is less than 1. And knowing what this number is and what I mentioned with gold and with aluminum earlier, so make sure you look at the very beginning of this video so that you understand that. This should be a metal with a very high density. So that would be something else that I would expect you to know. All right. That's great for number 2. Let's move on to problem number 3. Here we go. All right, so here is problem number 3. It says, calculate the final temperature in degrees Celsius of the one ring that is composed of 11.098 grams of metal. The specific heat capacity for the one ring is 0.129 joules per gram degree Celsius. You notice it has a high density since it has a very low specific heat, as we just learned in problem number 2, and is heated to 165 degrees Celsius and is dropped into Frodo's cup filled with 59.0 mils of water. The density of the water is 0.960 grams per mil, which is originally at 22.5 degrees Celsius. All right, so you should be able to understand which equation we're using. We're going to be using the thermal equilibrium equation under this one here. So the thermal equilibrium equation is here. Q of A plus Q of B is equal to 0. Okay, and you can call A and B whatever you want. I'm going to call A the ring and B the water in this particular case. Another equation that you could use is Q of A is equal to negative Q of B. So it doesn't really matter. This is an or statement, so I'll write that right here, or. And again, if you watch the very introduction of this video, then I describe what both of these equations mean. I highly recommend that you watch the very beginning of this video so you do have a full understanding of that. Okay, so what we're going to do is we're going to substitute in what Q is equal to for both of these Qs. And just recall, Q is equal to MC TF minus TI. Okay, all right. And so we're going to substitute in this component right here into both the Q for the ring and the Q for the water. So I'm going to write out that equation here. And so I'm going to start over here. We got M CP T final minus T initial plus MCP T final minus T initial is equal to 0. And we're going to call this one here the ring, and this one right over here the water. Okay, and if it says calculate the final temperature, so that's what we're trying to calculate is the final temperature. And this is the final temperature. That is the final temperature. That is the final temperature. So the final temperature of the ring is equal to the final temperature of the water. And that's when thermal equilibrium occurs. So effectively, we are solving for the final temperature right here, and we're going to call that X. That's what we're solving for. It is the same number. The final temperature of the ring and the final temperature of the water are going to be the same number. Okay. All right, so what we're going to do is we're going to plug in this information into here, and it says that we have 11.098 grams of the metal ring. The metal ring has a specific heat capacity of 0.129 joules per gram degree Celsius. And then the final temperature, TF, that's our X term, minus the initial temperature, and that's 165 degrees Celsius, plus the mass of the water. Now, you're not given the mass of the water, but you are given a volume of the water and its density. So you're going to use the volume, which is right here, and the density, the volume and the density, and the product of the volume and density is going to be the mass. Okay, so we're going to take the 59.0 mils. That's our volume, times our density at 0.960 grams per mil. And the product of these two, you should see that the units of milliliters cancels out, and I'm left with grams, which is a mass. Now I'm going to use the specific heat capacity for water, and that was aforementioned in this unit here, 4.184 joules per gram degree Celsius. Okay, and I'm going to slide this over just a little bit because I'm going to need all the paper here that I have. And then the final temperature final temperature minus the initial temperature, 22.5 degrees Celsius for the water. And we're gonna, I'm gonna put the equals 0 here on this left-hand side real quick so that you can see that. So this whole thing equals 0. Now what we're going to do is we're going to solve for RTF. So just going to highlight here again, TF. This is what we are solving for on this problem. So mathematically, this is probably the hardest problem in this unit. So what we're going to do is we're going to take the product of these two numbers and then distribute it over these terms. We're going to take the product of these three numbers and then distribute it over these terms. So this is what my next step is going to look like. The product of these two numbers is 1.43 and TF minus the TI, which is the 165, plus, and the product of these three numbers here is 237 TF minus the 22.5 and then equals 0. So one thing that I've done here, and I hope you've noticed, I've taken out all the units. I'm going to put the units back in there. We know that the final temperature is going to have to be in degrees Celsius. The final temperature is going to have to be in degrees Celsius. Okay. So hopefully you're okay with that. So now this is just a matter of doing like what I said. You're going to distribute this term over both the terms inside, going to distribute this term over both these terms inside. Okay. And so then our next step here, I'm going to slide this up just a little bit so you can see the next step here. And the next part here is going to be 1.43 TF, and that's really our X minus 236 plus 237 TF minus 5330 is equal to 0. Now what we're going to do is we are going to combine our like terms. And we are going to combine our like terms, and we are going to move the like terms to one side and the other like terms to the other side. That is the X terms to one side and the non-X terms to the other side, right? So we're going to have 238 X is equal to 5566. And now this is a simple matter of dividing both sides by 238. And now we're going to have X, which is equal TF. And that's going to be 23.4 degrees Celsius. So I've slapped those units back on there again. And this is the final temperature for both the ring and the final temperature for the water. Okay, and if we kind of zoom out on this problem here so you can see all of this, the entire problem in its entirety. What I want to do is state that you should see that the ring, the hottest thing, was at 165 initially, and the water was at 22.5 initially. And the final temperature for both must be in between those. It can't be greater than 165, and it cannot be less than 22.5. This value of 23.4 is somewhere in between these two, and that in between temperature is based on the mass and specific heat and the mass and specific heat of both. Since there's more mass and the specific heat is higher for the water, so both the mass is higher and the specific heat is higher for the water, that means that the final temperature is going to be most closely approximate to the water and not the metal. Again, the metal is hotter. It's going to lose heat energy to the ring. Okay. Heat always flows from the hot to the cold object. That's how heat always flows. All right. So we're going to zoom in on here, and that is this problem here. All right, just a quick little advertisement here. I am the Crazy Hat Chemist, and please watch my videos on YouTube. I greatly appreciate that. We're going to move on to problem number 4 of this worksheet. Here we go. Problem number 4. All right, so problem number 4, it says calculate the heat in joules, which is required to heat 10.3 grams of water from negative 15.3 to 109.6 degrees Celsius. All right. So the first thing that we're going to do is we're going to draw a rough, dicey, sketchy graph. And so that's what we're in charge of here. Just draw a rough graph. Not much to this graph. What's important here is that this is 0 degrees Celsius because this is water, and this is 100 degrees Celsius, again, because it's water. And so what we're going to do is mark on our graph our lowest temperature, that is below 0, and our highest temperature is above 100. So we're going to have to connect the dots. So we're going to have to do step number 1, step number 2, step number 3, step number 4, step number 5. So we're doing step number 1, that's right here. Step number 2, that's right here. Step number 3, that's right here. Step number 4, that's right here. Step number 5, that's right here. We're going to do all those steps, and then we're going to add them up together, and then that will give us our final value that we're looking for. All right. So step number 1 is based on the specific heat capacity for ice. So here we go. We're just going to cancel out units. We are looking for joules. That's what we want finally in this problem. Okay. All right. So here we go. We're going to pull out our ruler to make this look nice and pretty here. So we've got 10.3 grams of water, and the constant for this is joules per mole degree Celsius. So, and that was previously mentioned at the top of this whole entire worksheet. So we're going to be using those values. 1 mole of H2O is equal to 18.02 grams of H2O. That will now enable me to cancel out the grams of the H2O. Okay. And then our constant, which is 37.8 joules per mole degrees Celsius. That is our constant of which we're using. That enables us to cancel out the moles. And now we need our change in temperature. Okay, so our final temperature for this segment here, is 0 degrees. So it's 0 degrees Celsius minus the lowest temperature. The lowest temperature is negative 15.3 degrees Celsius. Okay. All right. Fantastic. Now I'm going to get an answer for this. You should see that the degrees Celsius, whoops, let's try that right, correct. Pen, the degrees Celsius cancels out. And what do we have for units? Joules. And what are we trying to solve for? Joules, ultimately. So that's only step 1. Step number 2 is going to be similar, but yet different. Step number 2 is going to have a different constant. Because it has a different constant, it's going to have different information here. You are starting with this 10.3 grams of water, and that mass will never change within this problem. Okay, and the constant for this segment is the heat of fusion, and that heat of fusion has kilojoules per mole of water. So 1 mole of H2O, and that's 18.02 grams H2O. That's our first thing that we're going to do. We're going to cancel out our grams right there like that. We're going to have our hard stop in between our next step here, and we're going to use the constant now. That constant is 6.01 kilojoules per mole. Notice that there is no there is no temperature term in this because this is this flat section here of this graph, step number 2 that we're doing right now. And hard stop here. And now what we need to do is convert the kilojoules into joules. So 1 kilojoule is equal to 1,000 joules. And then you're going to have the kilojoules cancel out, and you're going to have a term in joules. Again, that's what we're solving for, joules. Now we're going to do step number 3. Step number 3 is from here to here. That's step number 3. And we'll draw a nice pretty line here so that this works nicely here, hopefully. All right. So step number 3 is going to be very similar to step number 1, except that the constant is different. So we're going to start off with our 10.3 grams of water, and it's 1 mole of H2O to 18.02 grams H2O. You should again see that the units of grams cancels out. And now I'm going to be using the molar heat of water, and that is 75.40 joules per mole degrees Celsius. Moles cancel out. And the final temperature within this segment here is 100. The initial temperature is 0. So the final is 100 minus the initial temperature is 0. And these values have an infinite number of significant figures because I'm just noting the values on the graph. All right. And you should see that the degrees Celsius cancels out, and I'm left with joules. Perfect. Right. And then we need to do step number 4. Step number 4 is the heat of vaporization. So step number 4, and I'm going to have to slide this on up here to do step number 4. And here we go. Again, step number 4 and step number 2 are going to be very similar, except for the constant is different. So we'll have our 10.3 grams of H2O. And then it's 1 mole of H2O is equal to the molar mass. That's 18.02 grams of H2O. And that enables me to cancel out the grams of the water. Now we're going to use the heat of vaporization for water, and that's 40.7 kilojoules per mole. And again, there is no degrees Celsius in this because this is a flat section of the graph. And then we're going to convert our kilojoules to joules. So 1 kilojoule is equal to 1,000 joules. And the kilojoules will cancel out. And again, I am going to have joules for my units that don't cancel out. That's what I'm looking for. I'm going to slide back to this graph here, and we are going to do the final step, and that is going from this temperature of 100 to the high temperature of the final temperature of 109.6. So sliding this back up here again. So we'll do step number 5. And hopefully we can have this all on one slide here for you, so you can see it all. Equals there. And step numbers 1, 3, and 5, the odd number steps are going to be very similar. The only thing that's different on these odd number steps are the constants. Okay, so that's 1 mole of H2O, and that's 18.02 grams H2O. And then we're going to be using the heat of vapor, the specific heat capacity of steam. So that is 36.5 joules per mole degrees Celsius. And then we got our temperature change. Our final temperature is 109.6, and the initial temperature is 100. That's an exact value. You should see that our grams cancel, our moles cancel, degrees Celsius cancel. What are we left with? We are left with joules, of course. All right. So what we're going to do is we're going to plug all these values into our calculator. And we are going to have 3 significant figures on each one of these steps. The fewest number of significant figures is 3 on all of these. So this is going to be 331 joules. This is 3,430 joules. And notice I have 3 significant figures. That trailing 0 does not count. 4,310 joules. Again, 3 significant figures. The trailing 0 doesn't count. 23,300 joules. And then 200 joules. And this has a decimal here at the end because it's 3 significant figures. Now what we're going to do is we are going to sum up, add up all 5 of these numbers here. And then we're going to round the number to the fewest decimal places, which is going to be in the hundreds place. This is the least precise measurement right here in the hundreds place. So our final rounded answer is going to be 31,600 joules. And that is our final answer. Those trailing zeros don't count. Whew, that is an awesome problem. So what does this mean exactly? What this means is if you take 10.3 grams of ice that is at a temperature of negative 15.3 degrees Celsius and 109.6 degrees Celsius, it requires 31,600 joules to do that process. All right. Okay, sweet. So let's see if we can keep on going to problem number 5. So problem number 5 is right here. Problem number 5. All right, so says calculate the heat in joules that is required to heat 1.6 grams of water from negative 11.3 to 100 degrees Celsius of water, but not steam. So we're going to draw a quick little graph right here. And here we go. Defining this graph is 0 and 100 degrees Celsius because it's water. And it says that we have a negative 11.3. So that's where we are. And then we are going to say that we're going to heat this up to water, but not steam at 100. So we're right there. So we're going to connect the dots. We're going to do this one step, step number 2, and step number 3. So we're doing 3 steps on this problem, not the 5 like we did before. So we're going to divide this up into 1, 2, and 3 steps. Okay. Okay, here we go. Let's see if we can knock this one out of the park a little bit faster than the last one. So this one, we have 1.6 grams of H2O, and we have 1 mole of H2O, and 18.02 grams of H2O. That is the molar mass for water. And in this first segment, we are using the specific heat capacity for ice that was given initially on this worksheet at 37.8 joules per mole degree Celsius. And the final temperature at this segment here is 0 minus the initial temperature, that is negative 11.3 degrees Celsius. This is going to equal a number. You should see that the grams cancel, the moles cancel, the degrees Celsius cancels. What does not cancel, just like on the last problem, are joules. Okay. All right. That is step number 1. Let's hammer out step number 2 as far as the process. And then I'll just draw a line here for step number 3, since we're going to be doing that here in just a moment as well. Okay, let's straighten that out. There we go. Perfect. All right, so step number 2 is doing this segment from here to here, and that is the heat of fusion for water. So that's 1.6 grams of water. The mass never changes in these problems. 1 mole of water, and the molar mass of water, 18.02 grams of H2O. And the heat of fusion for this is 6.01 kilojoules per mole. And again, there's no temperature unit in here because this is a flat portion of the graph, but I do need joules. So 1 kilojoule is equal to 1,000 joules. What doesn't cancel out for units here are joules, so that's good. What does cancel out for units are grams, moles, kilojoules, and I'm left with joules. Step number 3. Step number 3 is going from here to here, and that is the specific heat capacity for water. So that's 1.6 grams of H2O and 1 mole of H2O and 18.02 grams H2O. And then we're going to use the molar heat capacity for water, and that's 75.40 joules per mole degree Celsius. And our final temperature here is 100. Our initial temperature is 0. So it's 100 minus 0 degrees Celsius. These are exact numbers right here because they're not given within the problem, and they are assumed to be exact. So what we're going to do is we're going to plug all this stuff into our calculator. We're going to get numbers here. Those numbers are going to be 2 significant figures. It's the least number of significant figures that I have in the numbers that were given. This is 38 joules. This is 530 joules. And this is 670 joules. Okay. These values are all in joules. We're going to sum up these numbers. We're going to use the least number of places, which is these 2 numbers have the least decimal places, if you will, and they are our final answer is going to be rounded at the tens column. Okay, so our answer is going to be 1,240 joules. And that is our final answer for this here. Hopefully that makes sense. Again, what that means is that it requires 1,240 joules to heat up 1.6 grams of ice that's initially at a negative 11.3 degrees Celsius to heat it up to water at 100 degrees Celsius. Again, that's not steam, that's water at that temperature. All right, cool. Let's move on to number 6. All right, here we go. Number 6. All right, number 6 is called a Hess's law problem. So you want to take a look at my lecture and make sure that you understand what Hess's law is. Okay, and Hess's law is relatively simple. Okay, the concept is that we need to add up these equations such that they equal the one that we want. So I'm going to put all our ducks in a row. That is all the arrows separating the reactants from the products in a row. And so what do I want? This is what I want. I want calcium plus carbon plus 3/2 oxygen, and that yields calcium carbonate. And so I'm going to have Ca plus C plus 3/2 O2, just like that. That's what I want. I want this, and I need to figure out what is the value for this right here. That's what I'm looking for. So I need to find a way to add up these 3 equations such that they equal this net equation right here. Okay, and so I'm going to do just little tiny steps and we'll figure out how to get this problem done. And it's really not too bad at all. Okay, so here we go. So I'm going to find things that are in the net equation, which are in these equations. I'll call this equation A, B, and C. So I need calcium on the reactant side with a coefficient of a 1. So do I see calcium in equation A, B, or C? Yes, I do. I see calcium in equation A. Is it in B or C? No, it is not. So that means that I'm going to be looking solely at equation letter A. Calcium is a reactant. Is calcium a reactant in equation A? Yes, it is. Calcium has a coefficient of a 1. Does calcium have a coefficient of a 1? Yes, it does. So that means that equation A is written correctly. So what I'm going to do is I'm going to rewrite equation A, and I'm going to keep all my ducks in a row, if you will. So it's going to be Ca, that's a solid, plus 2 carbons, solid, gives me an arrow, and CaC2 solid. Okay, so that's the first equation. And what have I done to this? I haven't done anything to this equation. I've left this equation alone effectively. So my enthalpy change for this is not changed. So I haven't changed this number at all. It's still the same number that it was before. I'm going to leave it alone. So it's going to be the negative 62.8 kilojoules. And we're going to come back to that in just a second. We're going to keep all our ducks in a row. We have 3 equations that we're going to do. Okay. So I'm going to take this numeric value and I am going to leave it alone. I'm not going to change that value here. So I'm going to say no change for this one. Okay. All right. Now what we're going to do is we're going to do another equation. And probably the next one that might make sense here is I can clearly see this CaCO3, that's calcium carbonate. I can actually see it in equation C. It needs to be on the product side with a coefficient of 1. It has a coefficient of a 1, so that's good, but it's on the reactant side, so that's bad. So what I'm going to have to do is I'm going to have to flip this equation in order to get the calcium carbonate on the product side. So that's what we're going to do. So we're going to rewrite equation C, and we're going to write the reactants as products. So CaCO3 plus CO2, and then we have CaC2 plus 2 and 1/2 oxygen. And so 2 and 1/2, that's actually 5/2 O2. I haven't included the states of matter. Hopefully you're okay with that here for the moment. And then what am I going to do with this number? Since I flipped the equation, what I'm going to do with this number is I'm going to multiply it by -1. Okay, that's what we're going to do. All right, so now I have, really what we're trying to do is we're rewriting all three of these equations to see if we can get what we want. And what we want is CaCO3, and we want the Ca over here. And I'm going to just write this out so you can see all this. Let's zoom this out just a tad. Here, now you can see everything. So I have this Ca, I have the Ca. I have the CaCO3, I have the CaCO3, just like that. And that's what I'm looking for. Okay, what I still need is I still need the oxygen here. And so I still need to figure out how to get that oxygen and the carbon. Okay, and so we're going to figure out how to get that now. So what we're going to do is look at equation B. So I haven't messed with equation B yet, but I do need to work with that. So you should see a number of different things that you can work with here. So you notice that carbon dioxide is not in this net equation. So therefore, it must cancel out. It must cancel out. In order for carbon dioxide to cancel out, it must be on the opposite side. So that means that the CO2 must be over here. Okay, just like this CaC2, that cancels out. See, there's one on the product side, one on the reactant side. These actually cancel out. So that's good because that's not in the net equation. Okay, and so I need to find in equation letter B how I need to get that carbon dioxide on the reactant side with a coefficient of a 1. It has a coefficient of a 2, and it's on the product side. So what we're going to do is we're going to flip the equation and multiply by 1/2. Divide by 2, same thing. Okay, so we're going to flip the equation. So we're going to put this carbon dioxide here on the reactant side. We're going to put the oxygen here on the product side, and we're going to multiply by 1/2. And we're going to put this carbon here, right there like that. And let's see if that works. So what we've done is we've flipped the equation. So that's multiplying by -1. And then we've divided the equation by 1/2. So we're going to divide the number by 1/2, just like that. Okay, and we're going to see if everything cancels out the way we want, and then we get what we want as well. Okay, and so let's deal with first things first here, and that is we got a carbon here and we got 2 carbons here. Well, all of this 1 carbon cancels out, and only one of these carbons cancels out. So I'm left with +1 carbon over here. And that is good because that is what I want. That's what I want. That's a good thing. Okay, and now I have some oxygen here to deal with. Now I do need oxygen, and I need actually 3/2 oxygens, right? Because ultimately I am trying to get this equation. This is what I'm trying to get. That's what I'm trying to get right there. They are the same thing, right? Calcium, calcium, 1 carbon, 1 carbon, 3/2 oxygen, 3/2 oxygen, and 1 calcium carbonate on the product side. I'm trying to get that. So I need 3/2 over here. How do I get that? Well, this is a 1 coefficient, but this is 5/2. So I'm going to say 2/2. So 2/2 on one side and 5/2 on the other side. The 2/2, so 5/2 minus 2/2, that's equal to 3/2. Now I have what I want. So this equation now matches with what I want. So now what I'm going to do is I'm going to work with the numbers of which were up here at the beginning for each of these. So that is, we have a -62.8. These are all in kilojoules. And then we had this -787.0. And then we had this 1538. And what we're going to do is we're going to leave this one alone. We're going to multiply this number by -1 and divide by 2, or multiply by 1/2. We're going to multiply this number by -1. And when we do all that, and then we add these three numbers up, we're going to get an enthalpy change for this reaction as equal to negative 1,207 kilojoules. And that is our answer for this problem. And that is a Hess's law problem. This is very similar to a puzzle. So you like puzzles? This can be a blast. If you don't like puzzles, then start enjoying puzzles. All right, so now we're going to move on to problem number 7. Here we go. All right. Problem number 7. Here we go. All right, it says for the decomposition of hydrogen peroxide, calculate the heat of the reaction. Let me get rid of this paper here. Calculate the heat of reaction in kilojoules for 2H2O2 yields 2H2O liquid plus O2. You will need to use some of the following standard heats of formation as well as additional assumed values. So this is an enthalpy of reaction problem here. Okay, let's see if this is focused here a little bit better. There we go. All right, so delta H for the reaction under standard conditions is equal to the sum of, let's see if we can do that sigma, the delta enthalpies for products minus the sum of the delta change in enthalpies for the reactants. Okay, so this is the equation that we're using. Okay, and so what we're looking at is this equation right here. I'm just going to rewrite it. 2H2O2, that's a liquid, yields 2H2O liquid plus O2 gas. Okay, so this is the single reactant. And these are products. So hopefully you recognize that part. That's really our first step here. Okay, so what we're going to do is get the enthalpy change for the reaction under standard conditions. And it says products minus reactants. Okay, and this is read as delta H naught, so that's N. And then this is P, that's P, and that's R. And so if you love or hate this radio station, that's NPR. NPR, hopefully that will get you to what this equation is dealing with. So it's the products minus the reactants. So the products are 2 water. So I'm going to have 2 moles of H2O. And then the value for this for H2O is negative 285.8. So negative 285.8 kilojoules per mole. Cool. Awesome. And it's the sum of the products. So sum of is plus sign. 1 mole of O2 and the enthalpy change under standard conditions for O2. O2 is an element. All elements in their standard state are 0. So this is 0 kilojoules per mole. Okay, and that is a defined value. Okay, so hopefully that works for you. I have mentioned this in class. Any element in its standard state is a big fat 0. All right, I'm running out of space here on this line here, but I'm going to do minus brackets the reactants. The reactants is just one reactant. And so it's 2 moles of H2O2. And the enthalpy change for that is right up here at negative 187.8 kilojoules per mole. And there are no other reactants. Cool. All right, I'm going to zoom out just a little bit so you can see all of this here on one part. And so we're going to take 2 times that value plus 1 times that value. This term goes to 0. Hopefully you understand that. Minus 2 times that. And make sure that you take account of that sign. So that's change in enthalpy for the reaction is equal to, and we're going to get a number here. And that number, I'm going to zoom this on up right here so you can see all of this. That number is negative 196.0 kilojoules. Because this value is negative, that means that this is exothermic. That is liberating heat. It's exothermic, all right? Boom. That's perfect. Done with number 7 there. There's the whole problem of number 7, just so you can see all of it together there. This is exothermic because this is negative right there. That is, it liberates heat, it produces heat, etc. All right, we got one more problem to do on this worksheet, and then we will be done with this worksheet, I believe. And then you can move on to the next worksheet, which is worksheet number 2. And then I actually do have a worksheet number 3 for this unit as well. All right. So here we go. Imagine you have 0.346 grams of aluminum at 25 degrees Celsius, and you increase the temperature until all the aluminum has melted. How much heat in joules does it take for this process? Some constants that might be useful are heat of fusion, heat of vaporization, specific heat, melting point of aluminum, and boiling point of aluminum. So this is very similar to the first couple of like 1, 2, 3 problems that we had done earlier today on this worksheet. Okay, and this is based on these graphs. So the graphs that we had previously were based on water, but they are based on the melting point, which is the melting point for aluminum is 660. And then the boiling point for aluminum is 2467. Okay, so what I need to do is find the lowest temperature. And what is the lowest temperature? So the lowest temperature is 25 degrees. So where are we? We are right here at 25 degrees, and we're going to increase the temperature until all of the aluminum has melted. So this is when aluminum starts melting. This is when aluminum is completely melted. So we're going to do steps number 1 and 2. And we're using the specific heat capacity for the solid, and we are using the heat of fusion. So we're just going to do those 2 terms, and then we've got our answer. Okay, so step number 1. Step number 1. Here we go. We got 0.346 grams of aluminum. And we got a specific heat capacity for aluminum for the solid, and that's 0.902 joules per gram degrees Celsius. That cancels out my grams. And the final temperature for this segment is 660. 660, there was a decimal right there, minus the initial temperature, which was 25.0 degrees Celsius. And that will enable me to cancel out my degrees Celsius terms, and I will be left with a joules for this. And then step number 2. Step number 2, I still have my 0.346 grams of aluminum. And then I am going to use what? The heat of fusion, which is 395 joules per gram. Wow, that just cancels out the grams, and now I'm left with joules. So this one, I'm left with joules right here. I'm left with joules right there. Boom. Pretty nice. I like it. All right, so once I do this in the calculator, I'm going to get this number, 198 joules. And then once I do this one in the calculator, I'm going to get it 137 joules. Both of these are rounded to 3 significant figures. I'm going to sum up these 2 numbers here, and I'm going to get the following number. That's 335 joules. And there is my answer right there. That is fabulous. All right, so we just did this video, and hopefully that works really well for you. And lovely, lovely. I hope you have a fantastic day, and please give me a thumbs up if you are learning anything in this unit here, and subscribe to my YouTube channel. I'd greatly appreciate that. Have a fantastic day, and see you next time. Bye for now.